In this video, we'll be looking at electrical quantities. We'll look at electrical charge, different types of charge carriers, and we'll also look at electric current, conventional current, and so on. So let's talk about electrical charge. Electric charge is that property of matter which causes a body to experience a force when placed in an electromagnetic field, right? So I'll repeat, electric charge is a property of matter which causes a body to experience a force when placed in an electromagnetic field, right? We won't focus too much on the properties of charge, but of course the relation between charge and current and so on, right? The electrical symbol for charge is Q. Now let's talk about charge and charged particles. There basically are two types of charged particles. We have protons, which of course are positively charged, and we have electrons, which of course are negatively charged, right? Now looking briefly at the simplified version of the atom, so we know that basically in an atom there's a centrally dense portion called the nucleus, which accounts for a significant portion of the atom's mass, which contains the protons and the neutrons, right? And outside the nucleus, on shells, which can be thought of as orbits around the nucleus, we have the electrons, which are more loosely attached to the atom, right? Now the protons, of course, are positively charged and they are strongly bound within the nucleus of the atom, whereas the electrons are more loosely attached to the atom, and as a result they have the ability to move from one place within the atom, and they also have the ability to move from one atom to another. And it is this ability of electrons to move which causes bodies to become charged, right? Of course, the movement of electrons is more pronounced in certain materials than the other. And of course, if we're talking about conductors or electrical conductors, we know that they basically consist of free electrons, right? So throughout this course, our concern about charge will basically be about that carried by electrons. So as I said before, we have two types of charges, positive charge and negative charge. And negative charge is carried by electrons, whereas positive charge is carried by protons, right? Now basically, if we talk about the total charge possessed by any particular body, then the total charge is equal to the charge on one charge carrier, and you multiply that by the number of charge carriers. So generally, that is how we calculate total charge. The total charge is equal to the charge on one charge carrier, and we basically multiply that by the number of charge carriers. Now, as we mentioned before, throughout this course, our primary look at charge will concern electrons, and essentially, when we speak about charged particles, unless otherwise stated, we'll be referring to electrons. So in any conductor, for instance, electrons are the ones which actually are the mobile charge carriers, and we'll be focusing on that. So essentially, with electrons in mind, we can think of the total charge as a charge on one electron times the number of electrons. And for that, the total charge can be expressed according to equation Q equals NE, where E represents the magnitude of the charge on one electron, and N, of course, is the number of electrons. And of course, the magnitude of the charge on one electron is given as E equals 1.6 times 10 to the minus 19 coulombs, which of course is a relatively small quantity. Now, the proton, which is positively charged, has numerically the same value, but of course, for simplicity, we often omit the sign, so we're just talking about the magnitude of the charge on the electron, 1.6 times 10 to the minus 19 coulombs. So if, for instance, we want to calculate the total charge, and we have the number of electrons flowing, we can simply multiply the charge on one electron times the number of electrons, and that will actually give us the total charge. So let's do a quick example. if in a particular section of a circuit we have, say, 1,000 electrons flowing, then the total charge flowing in that part of the circuit will be given by Q equals NE. So we have 1,000 times 1.6 times 10 to the minus 19 coulombs, and this will give us 1.6 times 10 to the minus 16 coulombs. So simply put, the total charge is equal to the number of electrons times the charge carried by one electron. Now, having briefly looked at charge, we'll also talk about electric current, and we'll examine the relationship between electric current and charge. Now, electric current, as we know, is one of the fundamental or base quantities. So the symbol for electric current is I, and the SI unit, of course, is the ampere. So electric current symbol is an uppercase I. Now, how exactly do we define electric current? An electric current is defined as the rates of flow of charge. So an electric current is a rate of flow of charge. So what exactly does this mean? It means that basically, in order for there to be a current or an electric current, there must be charge moving. So charge must be moving, and the rate at which these charges will move will determine the magnitude of the current which is flowing, right? So using the symbols for charge, Q, time t, and I, the formula or the equation which relates current, charge, and time is given by I equals Q over T. So this formula or this equation is a defined equation which expresses electric current I in terms of charge flowing Q and time T. And of course, from this equation we can actually make Q the subject. So from this equation we could get that Q is equal to IT. So if we have the charge flowing and the time for which the charge flows, we can actually calculate the current. If we have the current flowing and the time for which it is flowing, we can actually calculate the quantity of charge which must have flown past a given point in a circuit, right? Of course, if we talk about the SI unit, the SI unit of charge is the coulomb, right? So the SI unit of charge is the coulomb. Is the coulomb, spelled C-O-U-L-O-M-B, symbol is an uppercase C, and of course the SI unit of electric current, as for current, is the ampere, symbol A. And of course, as we know, the SI unit of time is the second. So if we look at the equation which relates current, charge, and time, we see that the current is equal to the charge flowing divided by the time taken. And since the SI unit of electric current is ampere, it would follow that 1 ampere is equivalent to 1 coulomb per second. So a current of 1 ampere is equivalent to a charge of 1 coulomb flowing for 1 second, right? Now, when we speak about the coulomb, 1 coulomb, of course, is a massive amount of charge. And that is why generally, for instance, in textbooks, you may see charges of the order of, say, microcoulombs and so on, because they try to be as realistic as possible, because 1 coulomb is a massive quantity of charge, right? So I'm going to say that 1 ampere is equivalent to 1 coulomb per second. Now, when we speak about steady current, right? Let's talk about steady current. What does it mean for a current to be steady? Now, as I mentioned before, current is defined in terms of the rate of flow of charge. So if a current is defined to be steady, it basically means that there's a fixed quantity of charge which flows past a given point per unit time, or in 1 second, in a conductor, right? So if we talk about a steady current of, say, 4 amperes, then this basically means that at a particular point in a conductor, every second 4 coulombs of charge will actually flow past that point in the conductor, right? So again, steady current implies that a fixed amount of charge flows past a given point in a conductor every second. And a steady current of 4 amperes would mean that 4 coulombs of charge flow past a given point in a conductor every second, right? So we looked at current and related the current to the flow of charge and time t. And of course, we spoke about steady current. Now, let's talk about conventional current, right? So we look at what is called conventional current. Now, in circuit diagrams, we often may see a battery, which of course is a group of cells, and we may see some other components in that circuit. So I'll draw a simple circuit on the board. So that's our battery, group of cells, and let's say in that circuit we have a resistor, right? And let's say we also have a lamp, simple circuit really. A lamp, that's a circuit, right? So that is our battery. Now from the symbol for a battery, we know the longer stroke represents the more positive terminals, or the terminals at the higher potential. So put a plus sign there. And the shorter stroke represents the more negative terminal, or the terminal which is at the lower potential. So put a minus sign there. Now, in circuit diagrams, we should always indicate the direction in which the current is flowing. And that direction is generally from positive to negative. So the current, or the conventional current, I, flows around the circuit from the positive terminal of the battery round to the negative terminal of the battery. Now, you might be thinking, how is this? Because isn't current the flow of charge, and the mobile charge carriers are indeed electrons, right? I mean, that is correct. So, as I said before, conventional current basically is taken to be the direction that positive charge would flow. Now, how did this come about? A long time ago, of course, when things were still being discovered, scientists would have been doing work in a whole other things. And they initially would have thought that basically the movement or the flow of an electric current was due to the flow of positive charge. And of course, in circuit diagrams, the indication or the direction of current was taken to be the direction that positive charge would flow, right? Now, by the time that had become accepted, after a certain time, that would have become accepted. And then only then scientists discovered that basically that the positive charges were more or less the more stable charges, or the more stationary charges within an atom, and the mobile charge carriers were indeed the electrons, which of course were negatively charged. So in reality, electric current is due to the flow of electrons. However, as I said, by the time that this discovery was made, it was already accepted as a convention that electric current was due to the flow of positive charge, and that is why up to this day we still show electric current, or what we call conventional current, flowing in the direction that positive charge would move. So in a circuit like this, the conventional current will basically flow in that direction, which is clockwise, whereas electron flow would be the opposite direction. So generally, the directional flow of conventional current is the opposite direction to which electrons would flow.